This video is going to cover electric fields and Gauss's law for special higher physics. Let's start by comparing the electromagnetic force and gravity. They have many similarities. You'll see they're both an inverse square law. The forms of the equations which describe gravity are very similar to the forms of the equations which describe the electromagnetic force. So if you keep that in the back of your mind, it should help you solve problems about the electromagnetic force by remembering how you solved similar problems for gravity. There's a couple of important differences. The electromagnetic force has positive and negative charges. Charges are kind of equivalent to mass in gravity. We only have positive mass. There's no such thing as a negative mass. Another important difference is that the electromagnetic force is actually stronger. You may find this slightly surprising as you're used to living on the surface of the Earth, and the Earth is a very massive body, so gravity seems like a large force. In fact, it's very small between, say, two humans. The electromagnetic force, on the other hand, is very strong, but because we have positive and negative charges that balance each other out in most everyday objects, we're possibly not as aware of it as we are of gravity. Let's just start by considering quickly how atoms work. We've got a positive nucleus filled with positive protons and neutral neutrons, and around that we've got these electrons. Now it's much easier to remove electrons from an atom than to remove anything from the nucleus. So it's these electrons that are responsible for most of the electromagnetic phenomena that we observe. Okay, later you're going to be looking at why don't these electrons fall into the nucleus if these are negative and these are positive, and there's a strong electromagnetic force attracting them. It comes down to quantum mechanics. Heisenberg's uncertainty principle won't actually allow them to fall into the nucleus. And another question is, why doesn't this nucleus fall apart if we've got lots of positive charges here and the electromagnetic force is very strong? Turns out that that's because of the strong nuclear force, which is even stronger than the electromagnetic force but has a much shorter range. Okay, so force, electromagnetic force, electrical force, is given by 1 over 4 pi epsilon naught Q1 Q2 over R squared. This is called Coulomb's law. In this equation, Q1 and Q2 are the charges measured in coulombs. R is the distance between them. Epsilon naught is equal to the permittivity of free space, which is 8.85 times 10 to the minus 12 farads per meter. You'll come across farads later when we do capacitance. It's the units of capacitance. Sometimes 1 on 4 pi epsilon naught is written as Ke, Coulomb's constant. You'll notice this has a similar form to the gravitational force. F is equal to G m1 m2 on R squared. They're both inverse square laws that depend on two masses or two charges in this case. So there's lots of similarities there. Now, you should know that this is for static charges. If charges are moving, they have a magnetic field associated with them as well, so there's an additional contribution to the force. So this is for the static case. So Coulomb's law applies to static charges. Now we're also going to consider electric fields. As you probably know, a field describes the force on a test particle. So F is equal to QE, where E is the electric field. So you can see from this that the electric field is going to be equal to 1 over 4 pi epsilon naught Q1 on R squared, where Q1 is the force which is generating that field. Now, the interesting thing about electric fields is that they do obey the principle of superposition. So the total electric field is just equal to the sum of all the individual contributions to the electric field from your various charges. So what this actually tells us is that if we know the point of every charged particle in the universe, we know the total electric field at every point in the universe, and so we could work out the electric force on any particle put at any point in the universe. Obviously, there's way too many particles in the universe for that to be of any practical value. Magnetic fields also obey a law of superposition. Let's have a look at how we draw field lines. Imagine that we have a charge here minus Q and a charge over here plus Q. Well, electric field represents the force felt on the test particle. We take our test particle as positive. So the test particle is going to feel a force away from the positive charge towards the negative charge. So we always draw electric field lines coming out of positive charges and into negative charges. They always come out at right angles as well. So in this case, we can draw an electric field line something like this. Let's calculate the electric field. First of all, in the situation where we have a charge plus Q, and then we have another charge here plus Q, and we have a point P here, which is a distance R from both these charges, and another point Q here, which is a distance 2R from these charges. Well, the electric field at P, a test particle put here will feel a force away from this plus Q here and away from this plus Q here, and those two forces are going to be equal and opposite. So overall, it's not going to feel any force at all because they're going to be balanced, and so the electric field is necessarily zero. Let's now consider a particle placed at Q. What we can do is work out the electric field due to this particle and then the electric field due to this particle and just add them together. So E at Q is equal to, due to this particle, 1 over 4 pi epsilon naught, and then we've got Q, which is the plus Q, over R squared. Now the distance in this case is 4R, so that's 4R all squared. And then what we need to do is add the contribution from this charge here. So this is 1 over 4 pi epsilon naught plus Q over 2R squared. So this is Q over 4 pi epsilon naught. Now we can pull R squared out as a common factor and we end up with 1 over 16 plus 1 over 4, which is Q over 4 pi epsilon naught R squared. And now we can put 16 as a common factor. This will be 4 over 16, so we'll end up with 4 plus 1, which is 5 over 16. So that will be the size of the electric field at Q, and it will be directed to the right. We should always give a direction as an electric field is a vector. Okay, another situation, calculate E again. So now we've got a charge minus Q here. Down here we've got a charge plus Q. This is a distance R. This is a square, so we've got another distance R here with plus Q. And first of all, we want to work out the electric field here at point P. So we can see that we'll have an electric field going upwards caused by this one. We'll have an electric field in this direction caused by this one, and caused by this one we'll have some electric field in that direction. So let's just call this 1, let's call this 2, and this 3 so that we can keep track of where everything is. Now for the superposition, probably the easiest way to do it is to add the electric fields at 1 and 2 and then add in the electric field at 3. Okay, so here's the electric field due to charge 1, which we can write as 1 over 4 pi epsilon naught Q over R squared, and the electric field 2 is equal to 1 over 4 pi epsilon naught Q on R squared again. So our resultant due to E1 and E2 is going to be up like this, these are equal, and so this will be 45 degrees. And when we work out this using Pythagoras, we end up with 1 over 4 pi epsilon naught root 2q over r squared. Okay, so now what we need to do is add this third electric field onto this one. So let's just draw this one down here. This is E1 plus E2, and it is at 45 degrees to the vertical. And then E3 is equal to 1 over 4 pi epsilon naught q. Now, the distance from here to here, this is r, this is r, so this distance is equal to root 2r. So when we square the distance, we end up with 2r squared. And this one is equal to 1 over 4 pi epsilon naught root 2q over r squared. Okay, and these are at right angles to each other, as this is 45 degrees with the horizontal. Okay, so we can use Pythagoras to get this resultant. So this is equal to 1 over 4 pi epsilon naught q. We can pull r squared out as a common factor too. And then we've got this one, which is 1 over 2 squared, plus this one, which is root 2 squared, and then we need to take the square root of that. So this is equal to q over 4 pi epsilon naught r squared. Now this is a quarter plus 2, and take the square root. If we put this all over 4, it ends up as this part is the square root of 9 over 4, which is equal to 3 over 2. So E total is equal to q over 4 pi epsilon naught r squared times 3 over 2. And then what we should do is work out the angle as well. So we can work out this angle in here using tan theta. This 45 degrees is with the vertical, not this angle straight in here. So tan theta is equal to opposite over adjacent, so that is equal to 1/2 over root 2. So solving that on the calculator, we end up with 19.47 degrees, and so you can give the angle, this part here is 45 degrees, so if we do the 45 plus 19.47 with the horizontal, that will give us our angle. Now with that same charge distribution, we've got another setup. We've got the minus q, the plus q, and the plus q, and we're asked to work out the electric field now at point q here, a bit confusingly named. So we know that the distance between these charges is r, and this is r as well. And so let's just switch colours. This distance along here is the same as this distance along here, and is equal to r on root 2, because this is a right angle triangle, and so r on root 2 squared plus r on root 2 squared is going to give you the r squared. So this is r on root 2, and we've got this distance here of r on root 2. So let's now look at the direction that all the forces will be, and so that'll be the same as the electric field. So this plus q will cause a positive particle to feel a force in this direction away from it. This negative q will attract a positive particle, and so that force will be that way, and this positive q will try and push the charge away, so will cause a force that way. And all these forces actually have identical magnitudes, because they've all got the same size charge, and they're the same distance from that point. So let's draw a vector diagram showing this. We'll add these two forces together. So they're going up like this. Now there's two of them and they're the same. So it's 2 times. Now the strength is 1 over 4 pi epsilon naught. And then we've got Q, same magnitude in both cases. So that's just Q over r squared. Now the distance in this case is r on root 2. So that's r squared on 2. So r squared, and then we can put 2 up the top here. And now this electric field is at right angles to that one, and it's got this same magnitude here. So we've got 1 over 4 pi epsilon naught 2q on r squared. And so our resultant is up here. To calculate our resultant, we can just use Pythagoras' theorem because these are at right angles. So we've got 1 over 4 pi epsilon naught q on r squared. That's the common factor. And then we have to add and square root everything else. So we've got a 2 left here, so that's 2 squared. And here we've got 2 times 2, so that's plus 4 squared. And so 2 squared, that's 4, plus 4 squared, that's 16, so that's the square root of 20. So we've got root 20q over 4 pi epsilon naught r squared is the magnitude of our total electric field there. Now what we need to do is work out this angle, so let's call that angle in there theta. And as this is a right angled triangle, you can see that tan theta is going to be equal to opposite over adjacent. So all these common factors will cancel out, and we're left with the uncommon factors, which is the 2 on the 4, or a half. So theta is equal to the inverse tan of a half, and that is equal to 26.7 degrees. So if we give the angle with the horizontal, this is 45 degrees here. And so we can say it makes an angle of now 26.7 plus 45 gives us 71.6 degrees with the horizontal as shown on the diagram. Now just some notation that you should be aware of. For uniform electric fields, we use rho to represent the volume charge density, which is the total charge over the volume. Sigma represents the surface charge density, which is Q over the surface area, and lambda represents the linear charge density, which is Q over L. So this is very similar to the mass densities. And also in electromagnetism, we can make the approximation when distances are large, when we're a long way away, that all the charge is concentrated in the center of the object at its center of mass, in much the same way as we could in gravity. In electromagnetic problems, you should always be looking for any symmetry that you can exploit to make the problems as simple as possible. So let's have a look at a bit of an example of where we would work out the electric field using the linear charge density. Imagine that we had a rod of length L and charge Q. So the linear charge density is going to be Q over L. And we want to work out the electric field here at a point P. So what is EP? We're told that P is a distance A from one end of the rod. To solve this problem, we're going to break this rod into little segments, each with length dx, and each of these segments is a length x from P. And we're going to work out how each of these segments contributes to P, and then what we'll do is we'll just add up each of those contributions. So we can write dE, the electric field due to this component dx, is equal to 1 over 4 pi epsilon naught dq over the distance squared, which is x squared. And now dq, the charge on this segment, is equal to lambda dx. So we can write this as 1 over 4 pi epsilon naught lambda dx over x squared. Now to get the total electric field, we need to sum up all over the rod. So the total electric field, we're summing up our x's from A up to A plus L. So from A to A plus L, 1 over 4 pi epsilon naught lambda dx over x squared. Pull all the constants out the front, we end up with lambda over 4 pi epsilon naught, and we're then integrating 1 on x squared, which will give us minus 1 on x. And this is from A plus L to A. So we can write lambda over 4 pi epsilon naught. Now instead of writing down this minus, let's just do these in the opposite order. So it's 1 on A minus 1 over A plus L. So this is equal to lambda over 4 pi epsilon naught, common factor A plus L, and we'll have A plus L minus A. So these A's will cancel out. Okay, let's continue up here. So we've got E is equal to lambda. Now lambda is just Q over L, and in this bracket we've got L on top, and this is over 4 pi epsilon naught A plus L. These cancel, and so we've got Q over 4 pi epsilon naught A plus L. Now let's just consider a couple of limiting cases just to check our answer a bit. If A goes to infinity, then we are a very, very long distance from this rod, and so we'd expect the electric field to go to 0. You can see if we put A goes to infinity in this equation, this does go to 0, which we would expect. Another thing we could do is put L equals 0, in which case instead of being a long rod, this is an incredibly short rod, i.e. a point charge, and so we'd expect the electric field to be the same as for a point charge, which it is. It's Q over 4 pi epsilon naught A squared, where A is the distance from the point charge. So that is what we would expect. Now we're going to calculate the electric field at a point P, a distance x from a disk. So we've got this point P, which is a distance x from this disk. This disk has a radius capital R, and it has a charge density of sigma. Now, doing questions like this, we always need to exploit the symmetry of the situation. So what we're going to need to do to answer this one is split our disk up into little rings. So each of these rings will have thickness dr, and we'll be working out how each of the rings contributes to the electric field at P. And then what we can do is sum up all the rings from the radius 0 up to capital R, and we'll end up with our total electric field at P. Okay, so with the rings, what we'll do is we'll consider a point up here on a ring and a point down here on a ring. So at P, you can see this point, because this is positive, it's going to have an electric field up like this, and this point is going to have an electric field down like this. This is some angle theta. And that's our theta there. So you can see the vertical, the y components are going to cancel out, and the x components are going to add together. So if we want to calculate the electric field for the ring, what we can do is we'll have 1 over 4 pi epsilon naught, and then we'll need to sum together all the dq's. So when we sum, we integrate, and this will be over the distance, which is fixed for this ring. Each of these little increments dr is a distance x squared plus r squared, the square root of that, from point P. This is little r here, the radius. So this is over x squared plus r squared. And we only needed to consider the x direction. In the y direction they cancel out, so we times this by cos theta. Okay, now cos theta, let's come up with another expression for that. Cos theta, using this triangle here, we can see cos theta is adjacent over the hypotenuse, so x over the square root of x squared plus r squared. So we can substitute this in here. So the electric field for the ring is equal to 1 over 4 pi epsilon naught. Let's just let the sum of all the charges around the ring be Q ring at the moment. In a minute we'll find out what that actually is. Over, now x squared plus r squared times the square root of x squared plus r squared. So that's x squared plus r squared to the 3 over 2 times x. So that's our electric field due to the ring, and that will be going out of the page and, well, going along the x direction, so away from the disk along the x direction. Now before we go on, let's just work out what Q ring is. Q ring. Now we know that this disk has a surface charge density sigma. So the charge of the ring will be sigma times the surface area of the ring. And what we can imagine is that this ring is a rectangle. It's got thickness dr and the length is equal to the circumference of the circle. So this will be 2 pi r, that's the length here, times sigma times dr, that's the thickness. So that's the area of that rectangle. So we can just put this in here. So our electric field of the ring is equal to 1 over 4 pi epsilon naught times x times 2 pi r sigma dr over x squared plus r squared to the 3 over 2. Okay, so now let's add together all our rings to get our electric field for the disk. So the electric field for the disk will be the integral, and r is going from 0 up to capital R, and we've got 1 over 4 pi epsilon naught x 2 pi r sigma dr over x squared plus r squared to the 3 on 2. Let's cancel off our pi's. Okay, so let's pull everything we can out the front. We've got 1 over 4 epsilon naught. This x is not a function of r. This distance isn't changing as we change r. Sigma is not a function of r. And so now I've got the integral of 2r dr over x squared plus r squared to the 3 over 2. Now the easiest way to solve this integral is by substitution. Let's let a equal x squared plus r squared, then dA dr is equal to 2r. So we can replace this 2r dr with dA. So this is equal to x sigma over 4 epsilon naught, the integral of a to the minus 3 on 2 dA. So that is equal to x sigma over 4 epsilon naught minus 2a to the minus 1/2. Instead of writing a there, let's write r x squared plus r squared because we haven't changed our limit, so it's easier. So we've got 1 over the square root of x squared plus r squared, and this is from 0 to r. So substituting in, we've got 2x sigma over 4 epsilon naught. Now to take into account this negative, let's do this one. So this is 1 over the square root of x squared minus 1 over the square root of x squared plus r squared. So this one here is 1 over x. We can write this as 2 sigma over 4 epsilon naught. If we put this x in here, x over x is 1, so this is 1 minus x over the square root of x squared plus r squared. So that's one way to write it. Now let's just consider the limiting cases. Let's consider what happens as x goes to infinity. If our point P gets a long way from this ring, we would expect the electric field to go to 0. So let's just check that. As x gets very big, this down the bottom, x squared plus r squared, gets very close to just x squared, so the r squared becomes irrelevant, and the square root of x squared is x, so x on x will cancel out, of 1 minus 1, which is 0, and so the electric field does go to 0 as x gets very big, which is what we expect, so that's a good thing. What we're going to do now is consider the charge distribution on conductors. Imagine that we have a conducting sphere and we're going to place positive charges on this sphere. Doesn't matter where we place the first charge, it can go anywhere. But then if we place another charge on this conductor, like charges repel, and so these are going to go as far apart on the conductor as they can. So they'll both go to the outside as far apart as they can. If we place a third charge on, these two will move around a bit and we'll end up with 3 distributed around the outside. If we end up with 6 charges, they'd be distributed like this evenly around the outside, as they're all repelling each other to get as far away from all the other charges as they can. So this actually always happens on conductors. On conductors, the charges always go to the surface and cancel out any electric field inside the conductor. So inside this sphere, there is actually no electric field. On a non-conductor, the charges stay where you put them. So you can get interesting charge distributions on non-conductors, but on conductors, the charges will always just be on the surface of the object. Let's consider a case of a conductor. Imagine we had a wire here with radius R1. If this wire has a charge density lambda, then we know all the charges are distributed along the outside of that wire. So inside, when R is less than R1, there are no charges and no electric field. And then let's imagine that we surrounded this conducting wire by a coaxial cable with radius R2, and here's radius R3. Now, we said last time that inside a conductor there's no electric field. The charges will redistribute to make sure that there's no electric field. So what actually happens is we get a negative charge density along this surface at radius R2, and this charge density is equal to minus lambda, because this one is plus lambda, and so they cancel each other out. And then let's say this coaxial cable had a total charge density of 2 lambda. That would mean that we'd have a charge density of 3 lambda at R3. So when we come and do Gauss's law, we'll be looking at things like this in a bit more detail. Okay, now just to be honest with you, we've said that the electric field is equal to 1 over 4 pi epsilon naught q over r squared. This is in fact a non-relativistic approximation of the electric field. If we want the real expression for the electric field is equal to minus q over 4 pi epsilon naught times ER dash over R dash squared plus R dash over C d dt of ER dash over R dash squared plus 1 over C squared dt squared ER dash. Okay, so what do all these terms mean? The minus comes about, really we probably should have had a minus here, but that's just because of the direction that an electric field goes. If we have a positive charge, then the electric field is going away from it at point P, so it's got a negative direction at point P. Now in the relativistic case, if charges are moving at a relativistic speed, we need relativistic corrections. And it doesn't actually matter where the charge is now. What matters is where was the charge when it emitted a signal, and the signals travel at the speed of light. So R dash indicates the distance between the charge and the point when light left the object, and ER dash, that's the unit vector in the direction between the charge and the point when the signal left the charge. So this term here makes sense. It's just nothing can travel faster than the speed of light, so what matters is where the charge was when light left it, not where it is now. These next two terms are a bit harder to explain. I'm going to use Feynman's words to describe this term. The next term is as though nature were trying to allow for the fact that the effect is retarded, if we may put it crudely. It suggests that we calculate the delayed Coulomb field and add a correction to it, which is the rate of change times the time delay that we use. Nature seems to be attempting to guess what the field at the present time is going to be by taking the rate of change and multiplying by the time that it is delayed. Okay. And then this third term, this is actually a radiation term. So it drops off it doesn't actually drop off with distance. So it's as though we were traveling along with a photon, so at the speed of light. So this is the radiation term. Now in this course, you won't be using this equation. You can just stick to this one, but just as you're planning on going on with physics, so that you've seen it, these are the relativistic corrections to this electric field equation. Okay, what we're going to look at now is Maxwell's equations. So Maxwell's equations are so important because they were the first time that electricity and magnetism were combined. So this was the beginning of grand unified theories. Before this, it was thought that the electric force and the magnetic force were separate from phenomena. And since Maxwell's time, we've managed to combine the strong and the weak nuclear forces in with electromagnetism. It's the holy grail of many physicists at the moment to try and discover a grand unified theory where gravity is described within the same theory as well. So Maxwell's equations really started it all off. So we're going to have a look at the differential form of Maxwell's equations. In this course, you're only going to be solving problems with the integral form, which we'll see later, but I'm going to show you the differential form because this is how they're often written, as they're very neat, very simple, and really very beautiful physics. So Maxwell's equations can be written as del dot E is equal to rho over epsilon naught. This is the electric field vector, so Ex, Ey, Ez. This is the charge density. Epsilon naught has its usual meaning, and this is the operator d dx, d dy, d dz. And so what this actually means, this is a dot product between this vector operator and the electric field here. So this really means dex dx plus dey dy plus dez dz is equal to rho over epsilon naught. So that's Maxwell's first equation. Maxwell's second equation is del cross E is equal to minus dB dt. Now, this is the vector cross product. This is the vector operator as written here, and this is the electric field. So if you were to solve this, you'd solve it just like a normal cross product. We're not going to write it all down now, but what you'd write down your matrix IJK, d dx, d dy, d dz, and then Ex, Ey, Ez, and use that matrix to solve this cross product. Okay, Maxwell's third equation can be written as c squared grad cross B is equal to dE dt plus J over epsilon naught. Now J, this is the current density. So flowing through a wire, you do the current divided by the surface area, the cross-sectional area of your wire. And Maxwell's fourth equation is grad dot B is equal to 0. Now let's just consider the static case where we've got no time dependence. So this is completely independent of time. This one in the static case is equal to 0. And in the static case, this dE dt is 0. So this is equal to J over epsilon naught in the static case. Now, this is very nice because it means that the electric field equations, 1 and 2, are completely separate from the magnetic field equations in the static case. So in a static case, we can consider electric fields and magnetic fields completely independently. They're not affecting each other. As you know, though, when charges start moving, we do get a magnetic field generated, so then there is an effect of the electric field on the magnetic field. Now what we'll see soon is that Gauss's law is actually just the integral form of this equation here. So it's actually a bit easier to deal with at the moment in the integral form, so we'll be using the integral form. But just before we do that, let's just have a bit more of a look at this electric field. Here we've split our electric field up into an EX, EY and EZ component. How do we calculate these? Well, our electric field is equal to 1 over 4 pi epsilon naught Q over R squared, and then we really should times this by a unit vector in the direction of the field. So how do we work out this unit vector? Well, in the x direction, we'll use the unit vector I, and the contribution in the x direction is given by Ex is equal to 1 over 4 pi epsilon naught Q. Now, in 3 dimensions, if we've got our particle at the origin and we're considering a point P, R squared is equal to x squared plus y squared plus z squared. That's just Pythagoras for 3 dimensions. And now the contribution in the x direction is equal to x over x squared plus y squared plus z squared to the 1/2. So that's just like when we take cos theta. Cos theta is adjacent, which is the x component, this thing, over the hypotenuse. So that's where this comes from, and this is in the I direction. EY similarly is equal to 1 over 4 pi epsilon naught Q. Now we can write this as x squared plus y squared plus z squared to the 3 on 2. Could have written this one that way, times y in the j direction, and EZ is equal to 1 over 4 pi epsilon naught QZ over x squared plus y squared plus z squared to the 3 on 2 K. I, J and K just have the normal meanings, the same as in maths, a unit vector in the x, y and z direction. What we're going to consider now is the electric flux. You saw magnetic flux in high school, and electric flux is very similar. In high school, you saw the expression EA or BA for the magnetic flux. So in university, we have a slightly more sophisticated expression. The electric flux still equal to the number of field lines cutting a surface. But how we can write it is it's equal to the integral over the surface of E dot dA. So E is the electric field, dA is each of the contributions to the total surface. This little circle here represents that we'll be considering closed surfaces. So if we have a surface which looks like this, we break it up into little sections with size dA. The direction of dA is perpendicular to the surface. Summing all the dAs over the surface will just give us the surface area. So let's consider a closed surface in a constant electric field. Here's our constant electric field. And here's our closed surface. Now, the electric flux through this surface is equal to the number of field lines cutting the surface. So all we need to do is count them. The problem is that the ones going out of the surface, we can take those as the positive ones, and the ones going in are negative. This is because if we draw dA, here's dA for this surface, you can see dA is parallel in this case, so this will be positive, whereas dA here is in the opposite direction to E. So while this makes a positive contribution, this one makes a negative contribution. So our total flux through this surface, taking these as positive and these as negative, there's 1, 2, 3, 4 minus 1, 2, 3, 4. So it's equal to 0. So it doesn't actually matter how we draw a closed surface in a constant electric field will always have the same number of lines entering the surface as leaving it. So the electric flux is always going to be zero. So the electric flux through a closed surface in a constant electric field is always zero. So that begs the question, how can we make the flux through a surface non-zero, the total flux through a surface? There's areas of this surface where it's positive, areas where it's negative, but summed up over the entire surface, the entire electric flux is zero. So the answer to that, how we can make it non-zero, is actually if we place a charge inside this surface. So let's place a positive charge inside this surface. So here's our positive charge. Now the electric field lines come out of this charge like this and cut through our surface. So we now have a positive flux through that surface. We can see that the flux is going to be proportional to the size of the charge contained within the surface. The size of the surface we draw is unimportant. The same number of field lines will cut it if we have the same size enclosed charge. So this brings us to Gauss's law, which in words states that the total electric flux through a surface is proportional to the electric charge contained within the surface. So mathematically, we can write this as the integral of E dot dA, that's the total electric flux over the surface, is equal to the enclosed charge, this is the charge enclosed within the surface, and the proportionality constant turns out to be epsilon naught. So this here is Gauss's law. So let's just use Gauss's law very quickly to work out the electric field due to a sphere with a charge plus q contained. So let's consider here a surface which is a distance r away from this charge. So we're finding the electric flux through this surface. So this, you can see that the electric flux over the surface is going to be constant because it's always at a constant distance from the charge. So we have E times the surface integral is equal to the q enclosed, which is this q, over epsilon naught. Now, we'll just provide some justification for this. We know that from Coulomb's law, the electric field at a distance r from a charge is given by 1 over 4 pi epsilon naught q over r squared. So this is what we're expecting to get. Now, what this tells us we need to do is take this surface area. So E times the surface area, which is 4 pi r squared q over epsilon naught, and so E is equal to 1 over 4 pi r squared epsilon naught on q. And these are in agreement with each other, suggesting that we've taken the correct constant of proportionality here. So let's solve a few problems using Gauss's law. Now with Gauss's law, it's important to always exploit the symmetry of the situation. What we want is the electric field to either be parallel or perpendicular to our surface increments so that we don't have to mess around with angles and we end up with an easy integral. So first of all, consider, this is example 1, consider an insulating sphere. So here's our insulating sphere. It has a radius of A and a charge density rho and a total charge given by capital Q. So we can see that rho is going to be Q over the volume of the sphere, which is 4/3 pi A Q. Now, part A of this question asks us to calculate the electric field at a point outside this sphere. Now what we need to do is choose a point outside this sphere. Let's choose it at a radius r from the center of the sphere. And so that we have a nice symmetric surface, we're going to take a spherical surface like this. Now, dA is always going perpendicularly out of this surface, so this is the direction of our dA increments, and you can see the electric field is going to be heading out of this sphere like this, always at right angles to the sphere. So the important point is that dA and E are always parallel to each other. So when we take the dot product, we end up with times cos 0 or 1. Okay, so let's use Gauss's law to work out the electric field in this case. We've got E dot dA is equal to Q enclosed over epsilon naught. Now the charge enclosed within this surface, we've got our entire sphere, which we were told had charge capital Q. So our enclosed charge is Q over epsilon naught, and we can pull this electric field out the front because the electric field is constant over the surface. So we can pull it out the front and we've got dA. Now what this integral means is it's the surface integral where we have to add up all the contributions to the area. So if we break this up into little dAs and sum them all over the surface, we're just going to end up with our surface area. So this will be 4 pi r squared E is equal to Q over epsilon naught. And so our electric field at this point, a distance r from the center of the sphere, is going to be given by E over Q over epsilon naught 4 pi r squared. Now let's just check that that's reasonable. As we send r off to infinity, we'd expect this electric field to drop to 0. You can see that does indeed happen. So this is a reasonable answer. Okay, part B says find the magnitude of the electric field at a point inside the sphere. So now what we do is choose a different distance r such that we've got some point inside the sphere there, the distance r. So r is less than a in this case. So what we need to do is just use Gauss's law again. We've got E dot dA is equal to Q enclosed over epsilon naught. Now what we need to do is start by working out this Q enclosed. It's not quite as straightforward as last time because we've got part of the charge in the sphere enclosed but not all of it. So the enclosed charge is just going to be the charge density times the volume enclosed, which we wrote our charge density was Q over 4/3 pi a cubed, and the volume enclosed is 4/3 pi r cubed. So this 4/3 pi cancels out, and we've got that this is Q r cubed over a cubed. So substituting this in, we can pull our electric field out the front because it's constant over this entire surface. So we've got E dA is equal to Q r cubed over a cubed epsilon naught, and when we sum up all the contributions to that surface, we end up with E times 4 pi r squared is equal to Q r cubed over a cubed epsilon naught. This will cancel, giving us that the electric field is equal to Q r over 4 pi a cubed epsilon naught. So that's our answer to B. Now part C says how would the answer to A and B change if the sphere was made of conducting material? So C, well, if it was made of conducting material, what would happen is that instead of the charges being uniformly distributed throughout the volume, they'd end up uniformly distributed over the surface like this. We'd have the same charge there, but it would all be found on the surface. So for part A, we've got the same charge enclosed, and so part A does not change. Doesn't matter if the charge is on the surface or spread evenly through this sphere. Now part B, on the other hand, if we look at how much charge is now enclosed within this radius, this green sphere here, there is no charge enclosed. So part B goes to 0. So Gauss's law actually means that within any conductor, there is no electric field. So that's an important point to remember. If you have a conductor, there should be no electric field within it. The charges will all distribute themselves to the surface, meaning that you have no internal electric field. Okay, question 2. Find the electric field at distance r from a line of positive charge of infinite length and constant charge per unit length lambda. Okay, so in this case, we have a long line of charge. The charge density is lambda, and what we need to do is choose some surface that we can use Gauss's law with to work out the electric field due to this. So to get a nice symmetric surface, what we'll do is we'll take a cylinder like this around our wire. So now our electric field lines are always going up away from the wire like this, and our DAs, if we draw them for the surface here, they're always perpendicular to the surface like this. On these end points, they're perpendicular. So at the ends, E and A are perpendicular. So that tells us that E dot dA will equal 0, because this will be times cos 90, which is 0. Okay, so what we need to do now is we use E dot dA is equal to Q enclosed over epsilon naught. Now enclosed charge, it depends on the length of our cylinder, so let's give our cylinder a length L. In this case, the total amount of enclosed charge is the linear charge density lambda times L. And we don't need to consider these circular cross sections, as we've said they contribute 0. So all we need to do is consider this part with the rectangular cross section. So the electric field over that surface is constant, so we've got E times the integral of dA, and the total surface area of this part, if we lay it out, it's just a rectangle, so it's just the circumference times L. So we've got E times 2 pi RL is equal to lambda L over epsilon naught, cancelling off the L's, and we end up with our electric field is lambda over 2 pi R epsilon naught. And that gives us our electric field at a distance r from that wire. And one final situation, now we consider that we have an infinite plane of charge density sigma. So this is a surface charge density. We've got positive charges spread over this surface, and what we need to do now is think of a suitable surface to take as our Gaussian surface. So what we can do is actually take any prism. Any prism is going to have contributions which are parallel and perpendicular to the electric field lines. So the electric field lines here are perpendicular to the surface like this. And if we draw our prism like this, then there will be area increments which are perpendicular to the electric field. So for these parts, we'll have E dot dA is equal to 0 as they are perpendicular. And then we'll have these parts on the ends where E dot dA does contribute, and it's cos 0, so it contributes fully. So let's do this. We've got the integral of E dot dA is equal to the enclosed charge over epsilon naught. Now let's let this end of this prism have area A. So the enclosed charge within this prism is given by the surface density, charge density times the area. So this is sigma A over epsilon naught. And now the electric field is constant across this surface. So we have E dA, and we've said that this area is A. There's two of them. And in both cases, the electric field and the surface increments are going in the same direction. So these two do not cancel out, they do add together, and so we've got E times 2A is equal to sigma A over epsilon naught. Now our A's cancel out. So that's why this shape didn't matter. It doesn't really matter what the area is. So we've got E is equal to sigma over 2 epsilon naught. And so this tells us our electric field at any distance from an infinite plane of charge. So note it doesn't drop off with distance, and that's because these lines are always parallel, and this is an infinite plane. In reality, we can't have an infinite plane of charge. Okay, and one final thing to do, we've said that E dot dA is equal to Q over epsilon naught. That's Gauss's law. And this is actually the same as Maxwell's first equation. So Maxwell's first equation we can write as del dot E is equal to the charge density over epsilon naught. So let's just use some maths to show that these two things are the same. What we can use is the divergence theorem, which is also called Gauss's theorem. So you'll probably do this in second or third year maths, but just to show you why these two are the same. So what Gauss's theorem says is that if we take the volume integral of the divergence inside a surface, so we've got, this is the divergence, this is our field, and that's the volume integral dV, and this is our vector operator d dx, d dy, d dz. This is equal to the surface integral E dot n ds. So what this is saying is that the outward flux of a vector field through a closed surface is equal to the volume integral of the divergence inside the surface. So this is a normal vector, normal to the surface. So that's, we took our direction of dA as normal to the surface. That is why. Okay, so what we're going to do is substitute this into this and show that we end up with Gauss's law. So the field that we're taking is the electric field. So we've got the volume integral of del dot E dV, and now according to Maxwell's equation we can write this as the volume integral of rho over epsilon naught dV. Now if we do the volume integral of the charge density, what we end up with is the total charge enclosed. So we end up with Q is equal to epsilon naught. So that's what this is. And going back to our divergence theorem, we can say that's equal to the surface integral of the field E dot n ds. Now, this E dot n ds, that's the same thing as our E dot dA, as we've got that normal vector contained within the dA. It's the direction of this dA. So we've now used the divergence theorem and Maxwell's equations to show Gauss's law. So this and this are equivalent, though it's much easier to use at this stage in this form.